I'm Antonio Sala, and in this video we will refine our discussion of the example 2 in these materials, and we'll discuss the interpretation of the concept of achievable or feasible reference, in the sense that in a generic case, when we do SVD decoupling and we do not control all the principal maneuvers equal to the rank of the matrix, then we lose something. We cannot control everything, and the things we can control are obtained by multiplying the set point by this matrix with scalings, whatever. And well, if you post a video and you do these manipulations, maybe you'll understand everything. But instead of doing this in the most general with the scalings, whatever case, we will concentrate in our example we developed in a previous video, so we can get the physical intuition on what we are doing. We had this system with a heater with 3 temperature transducers providing some measurements to my control. My heater had double gain in the central sensor, and so the least squares fit, the SVD decoupling, recommended controlling a weighted sum of the errors in which the weight of the central sensor was double of that of the extreme left and right ones. In this way, we are implicitly solving the least squares fit when my customers gives me 3 temperature set points, R1, R2, R3, and I wish to approach them in the least square sense, but I can actually control just one combination of the sensors, and it is this one given by the SVD decomposition of this transfer function, which has this single output maneuver that can be realized in this zero gain null space of maneuvers that cannot be achieved. So the projection of the set point in these directions is the thing that we will not be able to achieve. Then informing my customer on what my controller is actually trying to achieve is a good thing for my customer, understanding that the optimal way to operate the system is different to the one he is commanding. So how can we do that in our particular example? Well, so let us imagine that our operating point is 1.5 kilowatts at the input, and with an ambient temperature of 25 centigrades, we achieve 35, 45, and 35 degrees at each of the 3 sensors. Now, let us also imagine that my customer wishes to increment 10 degrees every sensor reading. So, he wishes to have 45, 55, 45 centigrades as temperature profile. Then we know that an increment of 10, 10, 10 is not feasible. If we go back to MATLAB, if my customer provides me with an increment of reference of 10, 10, 10, then the least squares solution would tell me to provide 6.6 kilowatts to my heater, well, in these scale units, whatever. And then when I multiply 1 to 1, which is the transfer function gain, by this 6.67, then I get, well, this actually achieved increment, 6.6, 13.3, 6.6. So the feasible increment is this one instead of 10, 10, 10. So the actual set point that will be achieved will be, instead of 45, 35 plus 10, I will achieve 35 plus 6.6, so 41.7. 45 plus 13, 58, and then 41.7. So that will be the actually achieved set point, so that it would be nice in my user interface to tell my customers that I will have a little less in here and a little more in there, because, central sensor has double the gain, so the best fit to the green points in the least square sense will be the pink ones. We got these numbers from a pseudo-inverse least squares reasoning. How do we get the same numbers from an SVD interpretation, which is in fact the same? Well, the SVD interpretation, here is the complicated way for a generic example. In our particular case, we can reason as follows. My control, for instance with integral action, will achieve zero error if this U transposed R, this is the error SVD, which is U transposed R minus U transpose Y, so this is Y SVD, and I will call this R SVD. Then, when Y SVD is equal to R SVD, this error will be zero. And if my controller in here has integral action, it will ultimately have that zero error. Then, if I now do the reverse change of variable to transform that Y SVD to physical units, then I need to multiply by U. The physical to SVD was U transposed, the SVD to physical is the it's U. So if Y SVD was equal to this, then multiplying by U, I get this U transposed conversion from physical user input to feasible, realizable, achievable set point. So multiplying by this matrix, the set point is what I need to get the achievable set point. So the arbitrary user set point 10, 10, 10 multiplied by this T matrix U transposed got me 6, 13, 6, which is exactly the same that the pseudo-inverse stuff did. And so this is what we see here in this block diagram, where also scaling to normalized plus minus 1 units has been also incorporated. But okay, scaling is just a trivial change of variables. The important things here are capital U and capital V from the SVD. And in this case, this is the transformation matrix I would multiply the reference with to get the pink points for whatever R1, R2, R3 the user would give me. Then in this way, I would communicate to my user that when he inputs the red dots as reference, my SVD controller, in this case my least squares fit controller, will actually try to fit the pink set points, because the red ones were not feasible, because the red ones had a non-zero projection over the SVD null space output directions. So removing that projections left me with the achievable reference with the pink dots here. So with this discussion and example, hopefully you have a better idea on what the achievable set point is and why it is of interest to show it to the end user, to let him know that we intentionally are not following what he is saying, because we cannot actually, given my process gains. So with this, we finish this video. Thanks for watching.